All right, so good morning, everybody. I'll share my screen here. Okay, so you should be seeing my my controls presentation, and this is the Pathways seminar, which has been there for quite a while and needs some updating. And the first update is we were talking about intelligent systems that are coming. Well, they're here, obviously, for some time now. And they are made possible by all the new computing technologies and the new technologies that we have on sensors and devices. Uh, Intelligent systems require feedback. There is a certain way to design, to do the intelligence. Uh, Feedback and controls deals with how we construct the algorithms that make all these devices useful, that take advantage of all the capabilities. And I'm going to give you a few examples, get some ideas of what's controls and how they're used, and obviously what are the courses that you can take in our program. Controls is not really one of the subjects that comes up very early in the process. The first time you see it is in 304, Signals and Systems 2. We see some applications of controls, but you've seen feedback everywhere. There is feedback in biological systems. There is feedback in most of the technology systems. And obviously, there is a certain formalism how we describe things so that we keep reusing tools, tools in design, tools in implementation, and being able to transfer the technology between applications. And in the small pictures, you see a lot of different ones, different applications. I have the aerospace, the usual aerospace, helicopters, and those are the applications that made feedback very well known, starting back in the 50s and the 60s, the newer applications. Then you see on the lower left side, you see some applications from disk drives. It's all technology now, but the concept is still there. Down below, there's a molecular beam epitaxy machine. And obviously controlling fabs, controlling big industrial plants, petrochemicals, and the more recent ones with biological systems and so on. So feedback means that we have a loop. We look at measurements from whatever we can measure out of the process. We call them outputs. We bring them back and compare them to some desired variables and generate input to the process. So that input is manipulated variable, something that we can change, like how much power we apply to a motor or a heating coil. And the dependent variable is the output of the process, which can be a torque coming out of the motor, or a position, or a temperature, and so on. And we try to control the process. What is the meaning of control? Stability is one issue, because by putting feedback, we affect stability of the system. We can stabilize or destabilize things, so one has to be careful. And perhaps one of the famous and very consequential instability examples was what happened in Chernobyl a zillion years ago. They were doing certain tests at the time. They destabilized the reactor and they had an uncontrolled reaction, which essentially led to catastrophic consequences. So stability is a constraint that has to be there, and then there is performance, which has to be defined in a meaningful way. And typically, we want the system to behave the way we expect in the presence of modeling errors, in the presence of uncertainty in general, disturbances, noises that come in the measurements, and so on. So feedback tries to make the system look good, even if there are limitations and there are errors in the way we model the system and we look at the system. Okay, so I included some more applications. I'm not going to talk about all of these in detail. I presume you do get the slides if you want to see a few things in some more detail, or you can always send me a question about any of these things. The typical problems that come up in feedback systems have to do with, well, first of all, system models, how we do certain things, how we make math essentially solve the problems that we are thinking about. So nonlinear dynamics are issues which create difficulties, mathematical difficulties in how we describe and solve problems. The dynamics which are not invertible, so we cannot just cancel things. Instabilities or time delays are things that we cannot invert. The time delays is probably the easiest one to visualize. If you want to cancel the effect of a time delay, you need to look ahead in the future. And that hasn't happened yet. So we need some different ways to manage time delays. They represent constraints on what we can do in terms of controlling a system. And in general, it is how much uncertainty we have in the system description, how many things we don't really know. And feedback has to respect the uncertainty. We have to do things within what we know, and we have to respect the uncertainty. There is a formalism, how we can describe that in math, and that's what the controls courses deal with. The last one of the bullets is also important. It has to do with the digital implementation. Pretty much everything these days is a digital implementation. There are several advantages in doing that. And maintainability of the system is one of them. It's not just how we design a certain algorithm that it may be easier to do it in digital versus analog. There are obviously some advantages in analog systems too, in terms of certain type of capabilities. But pretty much everything is done in a digital world. Which also has certain constraints and certain approaches that we have to use in order to make sure that the design works. So the typical process goes with modeling, simulation, and analysis. So we check the system, we model the system, we want to know how the nominal system works. In other words, the modeled part of the system, the one that we know about, and that is going to give us an idea what's realistic as an expectation out of that system. That part inherently means that in terms of controls and control engineering, people do have to at least be knowledgeable and appreciate what happens in other disciplines and in other types of technology. So, for example, you try to control um, an air conditioning system for a building, which can be part of a certain job. Well, you do have to understand how, what is the model of the heat transfer that happens in a building. And you try to control a rocket and how it aims and how it goes up and reaches the desired trajectory. So you need to understand rocket dynamics and how the engines work, what are the limitations and the capabilities of these engines. Cruise controls for car dynamics, and so on. So it is an interdisciplinary application. Now, in terms of the algorithms that go inside the control system, there's always some optimization being done, but there is well-known techniques and a procedure how we can do that. One needs to know that technology. It's not obvious or straightforward, so there is quite a bit of a knowledge base. The whole process is highly iterative, including the parts that I'm skipping now with the implementation and the evaluation. So the whole thing, we are going to iterate. Well, if we find that one of the steps does not perform according to specs, we would iterate to get a better solution. The important and the difficult part here is to make sure that what we iterate has some intelligence behind it. So it's not simply we are changing parameters at random and try to see if something else works better. We have to iterate with a certain intelligence. And the reason is that the number of free parameters, adjustable parameters, is huge. So mindless iteration doesn't really lead anywhere. We cannot blindly just iterate parameters. We have to choose carefully the directions. Okay, so different applications. As I said, aerospace is one that made controls quite famous in the 60s. In terms of historical events, the modern controls you start with telephony amplifiers. And so people needed to design repeaters for telephony applications, and those were high gain amplifiers. And if you were not designing the correct gain, the correct system, you were seeing instabilities. So that's where the theory began, but most of the developments that we know at this point, they came about with aerospace applications, flight control systems, and of course the space program that also produced a big leap in terms of the technology. Automation is in manufacturing has also a big chunk of control applications. You see a lot in biological systems. A lot of the things that happen in today's applications, they have to do with prosthetics, but not just the mechanical part, also the biological part. So mechanisms of biology systems. And power applications are also a big chunk of controls theory. Okay, so I'll leave the many applications there. You see, I think I jumped a bunch. I didn't want to go that far. Okay. So in terms of the control courses, prerequisites are circuits and the signals and systems. The first time you see controls is in 304, and there are two controls courses in the undergraduate program, 480 and 481. Right now, they're coming about alternating fall and spring semester. One is the 480 is the classical basic concepts of control systems. 481 is a little bit of that, but mostly discrete time applications, computer applications, and how we implement these control systems. So it's more targeted towards doing implementations in a lab, and it's the more applied version. And then there are graduate courses where we see more of, let's say, the elaborate part of control systems. It's the more of the high-level technology. Linear systems contains the basic driving engine of most of the algorithms. It's a course that's essentially required to do the rest. It has some of the advanced multivariable control algorithms and how they're done, what's the theory behind them, and some of the computations. And then there are non-linear. The ones that I have in red are the ones that are given more regularly, and they're more central to the program. So optimal control, neural nets, some filtering and stochastic processes, Kalman filters, that belongs to the essentials. And we actually introduced adaptive control in that basic sequence of courses because of demand from the robotics applications. Okay. In terms of faculty, it's you see us here, and the typical topics that we're dealing with are modeling, design, neural nets, adaptive systems, fault detection, and real-time applications, and then some quantum with Christian Arendt's quantum applications. Okay, and that's the slide I threw in earlier out of sequence, potential job opportunities, which is of course important for the student knowing which way to go. And maybe it's not really informative in the sense that, oh, well, this is pretty much every industry that you can find out there. But this is partially true. There are people with controls background who actually go into all these types of industries because there are applications which are controls related. Typically, we're not high volume as a discipline, but we do spread our tentacles pretty much everywhere. And there is a lot, there's a surge, at least in the last years, with robotics applications and automation in that part. Okay. So yeah, and I have a bunch of slides here with the new technologies and some ideas on what may be future applications where you can find applications essentially of feedback in the sense that we are, again, with the basic principle, we are measuring signals out of the system, and we are changing variables in the system to make sure that the system behaves as desired. So we take out the uncertainty, we take out the effect of perturbations, which are always present in systems. The thing that makes things a lot more difficult nowadays is the complexity of the new systems is so high that we can no longer expect simple models to work. We can no longer expect that, oh, well, we'll do a big factorial test and we'll figure out how our system works perfectly, and then we don't need any feedback. That theory, which famously was used for a while in the early semiconductor manufacturing, well, it's no longer possible. The complexity is so big that uncertainty and perturbations always come into system operations. So feedback becomes more and more integral in the operation. Okay, I think I'm done with my 20 minutes. I'll be happy to take any questions, or you can always send me email me questions that you may have later on. Okay. I see there is something on the chat. No.
Sorry, I'm just preparing for Dr. Iceland's slides. So, Dr. Sakoulis, there's a question in the chat.
Yeah,
How is
I see that.
Oh, okay.
Oh, we're going really in the deep very quickly. Now, when you have a nonlinear system that doesn't linearize very well, then you have to use nonlinear methods to be able to control that system. There are certain techniques where we try to blend classical concepts with scheduling. So there are applications which how should I put it? You put together a lot of linearizations of the system, and you try to find a controller that works on all of them, or you try to find a controller pattern that works on all of them, so a function that can work on all of these systems. However, all of these are typically sufficient conditions. So if they work fine, if they don't work, then you have to go and do something else. And there are classical problems of systems which don't fit that framework. Typical application is satellite that has reduced degrees of freedom. So you lost 2 jets out of the you need 3 pairs to control the satellite go everywhere, or an underwater vehicle that's the same. So if you lose one set of thrusters or jets, then you cannot control You cannot linearize the system to control it everywhere. But there are non-linear mechanisms that can do that. Statistics, no. We're not really stochastic. At least none of us here is dealing with stochastics very much. We understand what they do. Sometimes they come in terms of how you characterize a design, but typically all of us here, we are working mostly deterministic. Hardware evaluation. Well, depends how much homework you've done before the hardware evaluation. Your typical problem is, first of all, is how fast you can sample, how accurately you can compute things, which it has to do with how much you expect to do, how many computations you expect to do in a cycle. In some cases, you can do a lot. In other cases, not so much. You can claim that computers get faster and faster, yes. But typically, in every design, you're going to try to push the limits of your system as much as you can. So if you can work things faster, you probably do. So you need to make sure when you do the evaluation, you need to make sure that all of these things work, especially when you start having secondary objectives that you try to integrate after the fact. So now those are taking up some time in your computations. Noise, system noise in general, and some of the discretization can be an issue, which may or may not have been analyzed. So I guess that those would be major things. PLC, not really. PLC is not really my concern. PLC is, let's say, for low-level control systems. It's more on the automation side, as in, I'm going to schedule some operation, number one, number two, number three. So I see them more as a technology rather than something that you have to design in terms of engineering. Having said that, you have PLC systems which give you the capability to automate. So they give you the capability to take in signals, manage databases. So you can use a PLC system as a foundation layer for a control system. Maybe you can attach a processor to it. But mostly what I'm going to do is with microcontrollers or bigger controllers at that level, bigger versions of microcontrollers. So yeah, the PLC part is more of a technology level than engineering. Okay.
Okay, thank you,
And we
Kostas.
successfully made it before 10:30, and
Yeah.
Martin is extremely happy.
Thank you.
Thank you.
All right.
And I'm putting your email in the chat just in case anyone has questions.
Great. Thank you. All right, I'm gonna sign off, and you can take it from there.
Okay. Can we see the slides?
Yes, I think you do.
Awesome.
Good morning. So I'm Martin Reislein. I'm presenting for the signal processing communications. These slides were created in collaboration with Professor Andreas Banias and Wing-Chun Lei. These are the folks who primarily lead the signal processing communications. I'm also a member of the group, but I have to also disclaim, a brief disclaimer here, I'm also program chair for computer engineering. And the computer engineering presentation will be, I think, in 2 weeks. We'll then see, you will see me one more time. But today the focus is on signal processing communications. It's slightly related to controls, as you've just seen, but the main focus here is to getting signals across a certain distance to communicate and to manipulate those signals to extract insights. So you see here some of the examples of systems that we are considering. It can be a pacemaker, where essentially you want to manipulate a signal. The signal represents a physical system, say the heart rhythm, or an ECG signal that has to be manipulated, investigated to figure out a heart condition, and then this insight has to be put into some processing and then to control then via some control loop a pacemaker, so to stabilize the heart rhythm. Yeah, so that is a combination, if you see here, of controls and signal processing. So signal processing can play a part inside a control loop, where the control loops you've just seen in the preceding presentation. So next slide, please. Yeah, there's a wide variety of systems that involve signal processing communications that the phones use every day, weather, all types of medical, structural. It's mainly about sensors that can be embedded in everywhere in the world around us, and these sensors or sensing devices, imaging devices, the ultrasound, CT scanners, etc., will pick up signals, and then we have to process those signals to create audio or video or image insights that we as humans can then process and see. Yeah. So next slide, please. On the communication side, we have the phones, as we already mentioned. These operate mostly in a 4G, fourth generation, fifth generation transition phase at this point. The next wave is the sixth generation, 6G systems. It is still out and about debate as to what a 6G system should accomplish. Up to 4G, the focus has been mainly on human-to-human communication. So we as people speaking, communicating, consuming video, producing video, so audio visuals. From 5G onwards, the focus has shifted towards machine-to-machine communication. So it is a lot about, again, control loops, industrial control loops, controlling robots, manufacturing plants. And in order to ensure stability of those control loops, it's very important to have very short latency. So the communication latency has been minimized. And 5G has a target to keep the communication latency end-to-end below 1 millisecond. That's kind of a classical requirement of robotic control. That a stable robot operation would require less than 1 millisecond of latency. And so many of the protocols and architectures you see being developed for wireless systems target this 1 millisecond goal. Also mentioned here, of course, it's emerging topics, quantum communication, and machine learning plays a big role too to optimize all aspects of communications. So next slide, please. Yeah. There's also interactions between communications and the smart grid, the power grid. Essentially, a smart grid is integrated communications and power. Both are networks. There's a power grid, there's a power network that supplies electrical energy, and embedded in that is a metering infrastructure and a control infrastructure that transmits signals to communicate across distances and control these power plants and consumer devices. So it's really about integration of communications, controls, powers, all coming together. And communication is kind of the glue that keeps all these, merges all those things into a cohesive system, makes all the systems work. Yeah. So next slide, please. We've also some collaboration with the Arts and Media Engineering, the AME program. So arts performances and other interactive actions and displays will also require communications. So next slide. Okay, so here are our professors. We are a fairly large group. So in contrast to controls, signal processing communication is a fairly large volume, large group, numerous faculty, as you see here, with a wide range of topics and specializations inside signal processing communications, and also much higher student numbers that you may see in controls. Also want to point out here we are fairly balanced. This area is typically male dominated traditionally. However, we are very fortunate here at ASU to have a by the field that by our standards, the standards of our field have a reasonable gender balance. So the professors in blue are female. And as you see in terms of topic, is a wide range and a very fine-grained coverage of these aspects. That's the advantage of ASU. I mean, I did my PhD at UPenn, where I was also a fine electrical engineering program. However, the UPenn or at any of the more traditional schools, the professors in the department are fairly small in number, and they cover distinct areas, but they do usually not overlap and work across areas. So you have an isolated excellence in a certain topic at these traditional universities, but as ASU, you have excellence across all these topics, and you can integrate this excellence across these topics. So whatever your specific interest may be, or whatever your research may lead you, there's a very high chance that there will be a specialist professor in that particular very narrow slice at ASU. No? Next slide, please. Then what do these engineers do? So in terms of jobs, admittedly, right now the job market is a bit tight. However, generally, signal processing communications does quite well. There's always this classical competition here at ASU or in the Phoenix metropolitan area between circuitry, microcircuits, microchips versus communication signal processing. Yes, microchips are very important. So microelectronics is important. However, many of these microprocessors, microchips are part of communication systems. So both fields are very important. If you think of all the communications devices, communications is everywhere, also in all the military systems. And so there continues to be a very high demand, especially in the long-term prospect in the communication signal processing area. And as you see, the applications range from the military side, be it more radar imaging, the medical imaging, speech audio, and then networking broadly. So it's a very wide area. You're quite universal in the signal processing communications area because signals can represent so many different phenomena in our natural environment that with signal processing, you have a fairly broad base in the electrical engineering field. No? Next slide, please. Here are some examples of companies, and you see here many big names out of the semiconductor microchip industry, say Qualcomm, Intel, and it has been years where a large portion, is more than half of our graduates went to Qualcomm or Intel or these other names here. So this is a very active field in the Phoenix metropolitan area and our neighboring states, but also nationwide. Of course, right now with the Intel situation, it is a bit challenging. However, the long-term prospects are very good. with other players moving into the area. TSMC and again others will initially ramp up the microchips, microelectronics, but communications follows right behind because many of the microelectronics applications involve communications and signal processing. So next slide, please. Now getting the more specifics, the area, the courses in the area. So you have the 203 and 304 leading into the signals and systems area. Then 350 as a random signal theory foundation, mostly focusing on probability and random signals. These are building blocks, and based on those, we go then on the next slide to see the area-specific courses. There's the 407 digital signal processing, which employs those prereqs and to build on and build up digital signal processing. The communication systems, 455, is then mostly about preparing those signals to travel over distance. So there's modulation, coding, at a physical type of signal level. In 459, communication networks, that's what I teach typically. It's a kind of an unusual course in that it's not signal oriented, but rather it's protocol oriented. So 459 covers the TCP/IP protocol stack. We're building on the physical layer and then dealing with packets of information, how packets travel through networks, how the internet is structured, how internet protocols operate and interoperate. The 404 is in a kind of a special case of the 407, focusing on real time for all sorts of real time application, be media oriented or controls oriented. Any questions on these courses? I think we're rushing through here. No questions so far. Oh, no. So next slide then, please. Oh no, forward. Yeah. Then going on beyond these basic area courses, you see here a fairly long list of specialized topics inside the signal processing communications area. These are usually your graduate level courses. However, if you have covered the basics at the 400 level, you can go into those, and these would also be of high interest for the 4+1 program. Yeah, and again, wide range of coverage, very fine-grained, much more fine-grained than you would see many other universities, because we have a fairly large group of professors with wide range, very fine-grained coverage of the signal processing communication topic areas. Yeah.
We do have a question in the chat, Dr. Reislein.
Okay. Yeah, so 407 is the basics, and 404 usually builds on this. In addition, 404 has usually a lab component, so you're experimenting and dealing with the real-time processing aspects. It depends on the professor who's teaching it also. Oftentimes, there's a strong embedded systems component to 404 that you are working on embedded. So 407 is agnostic to specific technologies, the general principles. In 404, it's often then embedded into a real-time processing chip or embedded system that implements these principles and pays particular attention to real-time type of processing. Synchronization issues play a role, timing issues play a role. So it is a more specific twist to 407. So if you want the basics, 407 first. If you then want to go into more multimedia, embedded systems, then the 404 is a good addition. The 455 is the more, it's a bit decoupled from those, and it's really its own standalone communication systems. So you have to take signals, you have to process them, and for communications, you have to then process them in a very, very specific manner to prepare them for transmission over antennas and on them over the air or over mediums such as fiber or coax cable, and the time domain characteristics and the frequency domain characteristics of those signals is very, very specific for communications, and this is specifically covered in 455. This is a big topic. There are many, many issues to watch out for, and therefore 455 is its own course, specifically for communications. All right, so next slide, please. I think we've covered that one. Yes, there are more classes. As you see, the list is even longer. Again, this is very broad. This is overall and very fine-grained. So we have a very strong group of professors in signal processing communications with a wide range of coverage. It's really, really world-class in terms of coverage and quality. Next slide, please. Oh, in addition to those more settled courses that have regular numbers, there are many emerging topics. We call them also special topics here, these 598 classes. Usually these cover topics that are not so well established yet, that there are say standard textbooks and standard course numbers established yet, but the last of these are new topics that are just picking up steam. Oftentimes these are very hot for the job market. So if you want to distinguish yourself on a job market, these can be very helpful. Oftentimes also these are taught by new professors who are setting up their new research groups. It's a good way also to get into a new research area with a new research group of a new faculty member. And again, in terms of the breadth of coverage, ASU is unparalleled in the field. So it is strongly recommended to take a look at these, and you will really stand out, both if you're looking to go on for grad school or on the job market. Next slide. Speaking of grad school, it has kind of the bachelor is good, but signal processing communications is such a complex field that the trend has been towards mostly master hires. Many of the big corporations in the area will primarily hire master students, or will want to have undergrads and trained and going through internships and progressing then towards a master's. But maybe if you get hired as an undergrad and internships and get your foot in the door, many of these companies will then push the employees to get a master's degree. It's just because they see really foundations in the signal processing communications that are quite broad. There's a lot to watch out for, and so masters is very important. Also, PhD is becoming important. Several of the big corporations will want PhDs, this very specialized knowledge and research experience in the signal processing communications area, aside, of course, from the academic institutions requiring PhDs. At ASU, we have a direct PhD, that's also to point out for, so you can, it's quite efficient. You can get both the master's and PhD in 4 years. Some students are even faster than that, depends also on the research topic and how well research is progressing. If you're very ambitious and lucky with the topic, it can go faster. There's also most of the PhD students are supported by either research assistantships, and there are also fellowships that support PhD students. Good. Next, any questions on this? Very important topic. Also 4+1, very important. We have a very strong 4+1 program. Again, this is reflected in the fact that in signal processing communications, the master's is quite important in terms of career progression. Good. So next slide, please.
That's your last slide.
That's my last slide. Okay, good.
Yeah.
Yeah. So again, just underscore internships are important in the field. There are rich internship possibilities, and then it's fine and perfect and wonderful to finish up the bachelor's, but never too early to start thinking about the masters in the signal processing communications area. And yes, there's a special 4+1 and a grad program then. Oh, it's next week already, so it's 2 weeks. In 2 weeks is fall break. Yeah, so it's next week where I will then also speak about our wonderful computer engineering program. Any questions?
Thank you, Dr. Reislein. I don't see any questions in the chat, but we'll see if any come in. And then in 2 weeks, we will have a pathway seminar on senior design and data science. Do we have anyone here who's in ASU 101 with Dr. Reislein? There's a question in the chat. What book is used for 455?
Oh, good question. I don't know off the top of my head. I've used to, could be, I'm not sure. I think is Dan Bliss teaching us currently?
Yeah, it's probably Dan's book.
Is Dan's book then, right? So Dan Bliss I think wrote his own book and also did Dan Bliss, created a lab for the course. It's quite neat, very up to date, very current, and he has a great book on this.
And note that 455 is only offered in person at this time. Dan is working on getting that set up for online, but his in-person labs require some specific equipment. So he's working on translating that over for an online experience.
Yeah, but strongly recommended. So 455 is kind of the glue between signal processing happening locally on a computer and then going out into the world with those signals and getting them over a network. So without 455, nothing could get out of your local box into the world. Yeah, so very, very important. Yeah. I mean, all the components are important, right? You have to have the entire chain, and ASU covers this entire chain, starting from the processing, computer engineering, the signal processing, specifically communications, to networking, to antennas, and then beyond that. Yeah. Oh, complete subject area. Define complete. What does complete mean? Among you, I'm not sure what complete means here. CEE is a very wide range, right? It's really from physics, natural sciences, to all the way across these various disciplines we've seen now to computers and computer science. So, and on to industrial engineering, if you will. Yeah. Or if you're looking to do a PhD, this is a very personal decision what PhD topic to pick. I think you should really consult with the faculty of the main areas. Yeah. In EE, we have, as you see, there's different pathway seminars. Each pathway has a corresponding faculty who mentor PhD students in each and every of these pathways. So it's hard to pick one over the other. Many factors play a role: personal interest, background, job prospects. So it's really hard to pick. They all are very good. Yeah. maybe Lynn is the main resource from advice. I mean, again, our advisors have guided students through this difficult process of finding your pathway many times. So Lynn, any insights?
So I would say signals and communication is fairly broad because it contains both the signals and the communication aspect. Some schools split them apart. I see a lot of students within the signals and communications area also taking RF circuits and EMAG classes. We have students in the signals and communication area that work with NASA and JPL in the School of Earth and Space Exploration. So there are a lot of applications. There's also a close crossover to the control systems area, which is why controls and signals has the same day for pathways. We have these buckets, these pathways, just for general categorization, but there is a lot of flow between all of them. For example, if you're doing signals, you might take some power classes if you're going to be doing any space applications. If you need to do any radiation hardening, stuff like that. I would say EE in general is probably the best degree within engineering if you compare it to mechanical and computer science. And that does also include our computer engineering, electrical engineering degree. Electrical engineers are just extremely versatile. And we see the demand for them across the board, all industries, with unwavering popularity. You'll see in the news a lot of, lots of layoffs within Amazon, computer science, that sort of stuff, but EE remains really stable. And it's just going to continue to increase as our EE students gain more knowledge within Python coding and quantum engineering.
Yeah, so EE is a dynamic field. As data science, as machine learning, deep learning evolved, EE has absorbed many of these emerging topics, learning into the EE discipline-specific aspects. So machine learning is not everywhere in EE. And the same applies to data science. I mean, there's this new data science concentration pathway that has just been established, but across all the pathways, you see more and more data science-y approaches being incorporated. So it's a very traditional old discipline, but at the same time, it stays young because these new technologies and approaches are integrated into whatever EE specific is going on.
Great question, great conversation. Thank you, everybody. We are just about at our 11 o'clock deadline. So if there's any more questions, please put them in the chat. Otherwise, you can always reach out to Dr. Reislein by email.
Sure.
Or advising either undergrad or grad. Thank you, Lynn. And we'll look forward to seeing you next week.